Alright, so we're here to talk about one thing in particular, and that thing is LiDAR. And later on we're also going to talk about this little guy. But first, let's talk about what LiDAR actually is. LiDAR is a form of remote sensing, and a remote sensor is a device that takes data about some specific target, in this case it's testudo, like we already talked about, and it does that without physical contact with the thing it's trying to scan. So, as we see in this image, you are sending out some kind of electromagnetic radiation, and you're receiving some kind of reflection from an object. Now, that only occurs in active remote sensing, which we have here. Passive remote sensing just doesn't have the emission part, skips all that, and just collects radiation that's naturally reflected. So, let's talk about the sensor that we'll be using to scan testudo, and that's this little guy right here. Now, as an active remote sensor, every LiDAR sensor requires both a receiver and an emitter, and in our case, the receiver will be a Raspberry Pi camera, which will highlight in blue, and a line laser, which will highlight in red. Now, the reason we're using a line laser is because if you use a single point off a one-point laser, the way our sensor is configured, which you'll see later on, you only get one data point. If you use a line laser, you get a point for every single pixel of that axis of the picture. Now, these two things are held together by the green plastic mount that you see in the picture there. Now, I did redesign this mount compared to the one that was standard for the class so as to make it a little more easily 3D printable. Overall, what I ended up doing was cutting the print time by roughly an hour, give or take, and that's on my machine, so it may be a little more time cut on others. And it also removed almost all the support structure so that surface features remained relatively smooth and unimpeded. The other benefit is that I was able to add a small block on top of the laser so that I could actually thread that and put an M3 bolt in it to secure the line laser, as opposed to epoxying in place, which allowed me to adjust the laser later on. Now, since we've made this ourselves, we can specify the dimensions of it, and in this case, we have set it so that both the receiver and the transmitter are separated by exactly 12 inches, and this makes it much easier for us to calibrate the sensor later because we know exactly what the separation is between them. And the way this sensor works, that's very important. To explain why that's so important, let's reduce this down to the simplest thing we can. 3 colors and some random pictures in Microsoft PowerPoint. So here we have the sensor mount in green, the laser line itself in red, and the field of view of the camera in blue. Now, when we're zoomed this close in, you can't really see what the actual effect of the geometric LiDAR is, but if we zoom way out, say for example this far out, you can start to see how this thing works. So, at a certain distance from the sensor, the line laser enters the field of view of the camera, and ever after that point, the farther away it is, the closer to the center of the camera the line laser appears to be when you look at the image. So, if we know how far apart the two are, then we can deduce, based on how far that line laser is from the center of the image, how far away the thing the laser is on is. Now, the one catch with this is that we have a random variable floating around, and that's the field of view of the camera. So we don't necessarily know, on first glance at least, how far from the sensor a target actually is when we look at just the LiDAR light shining on it. So we're going to need to calibrate this somehow, and we're going to do that with images like this one. This is one of a whole set of images that were taken to calibrate the exact sensor used to scan testudo, and this one in particular was taken 60 inches away from a wall, or 5 feet, essentially. And of course, that wall wasn't perfect. There was an air conditioning unit on it, and there's a little hole between the two, which is why there's that one divot in the middle of the line. So you can pretty easily tell that the sensor is working from the way that divot shows up in the scan. And if we take a whole bunch of these and combine them and get some distance data off that center point along the central axis of the picture, then we can take those points and use some variables called rho and RPC, which are essentially an offset and a gain, in order to get some calibration, and that curve is this. Now, this is obviously after some fine-tuning of rho and RPC, but eventually we do get a pretty accurate representation of distance. So we can then take our LiDAR scanner out and look at some object in the field, take some scans, and get some quality data off it. Now this is where we come back to testudo, because as we mentioned earlier, He's our target in question. So we're going to go out to him and get some data. And the way we're going to do that is using a script called datacollection.py, which is a Python script, which essentially asks for an inertial measurement unit angle. And in that case, we're getting this angle from a phone, and then takes a picture with that angle embedded in it, so that later on we can process those images and create a point cloud out of them by getting one data point for every pixel along that laser line. Now what you've just been watching in the background this whole time has been me taking one of a set of images in order to scan Testudo, because of course one image does not a scan make. So on each side I took images every 2 degrees for the base, since it's a relatively simple structure, and since Testudo's shell is dramatically more complex, I took images every single degree. Now, of course, as we mentioned before, these angles are taken off the inertial measurement unit on a phone, so they're far from perfect. But, that being said, they're still accurate to within roughly a degree, so we can consider this a fairly accurate scan. So now that we have all of our images, the real magic trick here is to try and get range values off of them, and that involves figuring out where that laser dot of each part of the line on every pixel actually is. So to do that, we're going to use something called computer vision, which is a series of techniques whereby computers can analyze images in real time, or at least semi-real time depending on processing power. Of course, we don't need to do this in real time with the Testudo images. We already have them. We can post-process them in batches. But what you're watching right now in the background is essentially the principle we're working on here. The computer's looking for the green dot in that image, and it finds it and keeps a track of it. And what we're going to do is take every single one of those images from all angles, and we're going to put them through a script called datageneration.py that will find the dot within all of those images and then export them all as a point cloud that we can import into MATLAB. But before we get to MATLAB, we have to talk about the one hitch with Testudo, and that is a part of the LiDAR equation called the scattering coefficient. And Testudo himself, not the base he's sitting on, but the actual turtle, has a really, really problematic scattering coefficient. And the issue with this is that he's both dark and reflective, so not a whole lot of the light that's shown on Testudo actually makes it back to the camera. In fact, almost none of it does. The images that come back look like this. And so in order to try and get any data at all off of Testudo, the option essentially was to magnify the amount of red in the image, and that was done using a version of the script provided by Dr. Mitchell, which essentially went through the image pixel by pixel, and if the pixel in question had enough red in it relative to the other colors, it would make it all red, and if it didn't have enough red relative to the other colors, it would make it all black. So after this, they essentially turned the image into only laser line where there could be laser line or no anything whatsoever, and eliminated all the background noise in addition to amplifying that color line. The one downside is that it did slightly thicken the line, so it made the data a little more fuzzy, but we did get actual data off Testudo as a result. So now that we have all of our images processed and everything's all set, we can move on to actually putting these little point clouds together in MATLAB. And so what you're watching right now is the script to do that. The trick is that every image is recorded from the perspective of the camera, and so every point cloud comes from the perspective of the camera when it's in that place. So all the point clouds are right on top of each other when you first import them, so we've got to move them around. So the first part of this is going to be just a series of transformation matrices, just common linear algebra, by which we're going to rotate every one of those XYZ vectors or point sets and move it around a little bit to move all those point clouds into position. And once you get all those point clouds in position, it looks a little something like this. Now there's a lot of noise in this picture, so what I essentially did was figured out where the rough edge of Testudo was, and anything that wasn't really within the bounding box that defined the statue itself, that got converted into a nan, or not a number. And when you plot nans, they don't plot at all, so they all disappeared, and you get a much more filtered point cloud looking a little something like this. Now, while obviously this is still not perfect, and we're still missing quite a bit of data from the shell of Testudo, Here's an image where they're color-coded so you can see what is the actual testudo statue itself versus the pedestal it's on. It still looks a good deal like testudo, and if you know what testudo looked like, you'd have a pretty easy time identifying it. Now, since visualizing the point cloud is a little bit gross in MATLAB itself, we're going to move over to MeshLab so that you can get a better view for what this point cloud actually looks like and whether or not it's accurate. While I think it is, you may of course disagree if you like. So, the trick also with MeshLab is that you can convert point clouds into 3D meshes, and that's the next part of this goal. And it's not one that went particularly well, just to preempt things. It came out looking like this. Obviously, that looks nothing like testudo in any way, shape, or form, which is kind of a problem. But in the end of the day, probably what the issue is the fuzziness of the walls caused by the conditioning script. And unfortunately, that's a little bit unavoidable because without that script, you don't really get data. But with it, you don't really get a mesh. So one possible solution to this would be to cull a whole lot of those data points, though I haven't been able to get that to work yet. Or just to take a heck of a lot more data points and try and get an even denser mesh, which I haven't had a chance to try either, unfortunately. So those are both avenues for future success or progression. Now, all that being said, it's still worth going over how we ended up getting to this mesh in the first place. And so let's just flip through really quickly how to use MeshLab. So the first thing we're going to do is compute the surface normals. Of course, we need to go to the render menu and set them to be visible. Now, once we have those surface normals visible, we simply pull up a submenu and select a neighbor count until we get all the surface normals pointing in the same direction. Now, not the same direction as in all along the x-axis, pointing in the positive direction, but the same direction as in pointing out of where the object would be were the mesh to exist. And this is just to give an idea to the algorithm that we're going to use as to where the surface actually is and which direction it's facing. And this is the problem that we're running into, is that the front face of the mesh has its normals pointing in the wrong direction, which is why it has that cavity in the middle of it. But once we get all those normals generated, they look a little something like this. Now, once we've played around with the neighbor count enough in order to get all of those surface normals pointing in the same direction as in out of the object, then we just use a surface reconstruction method, preferably the Poisson method, and that will give us our final mesh. Now, in order to make this 3D printable, obviously none of the faces are going to be perfectly flat, so it won't fit on a 3D printer build plate, and it won't stick. So simply cut off the bottom of the mesh and then replace that by filling the hole with a flat mesh, and that will get you a 3D printable mesh of whatever you've tried to scan. And so that's pretty much a wrap. We've taken a actual LiDAR sensor and we've gone and we've scanned testudo. We've used that laser to bounce it off the target and get some data back, use that data in order to get a point cloud that is dimensionally accurate and represents testudo, at least mostly. Though we haven't quite created a perfect mesh. But hey, we got pretty close. So thanks very much for watching. I appreciate it.